And petrology means, Petros means rock. So this is the rock, how we try to explain different type of rocks depending on the content of the mineral content, and also where they have been built and so on. So we have three rock types which we can start to discuss. It's the magmatic rocks, which are creating all these minerals we can see originally. They come from the inner side of the earth. But then we also have sedimentary rocks. So when the rain falls on the rocks, it will dissolve. You know how fast a rock will dissolve? A granite, if it is raining on this granite for 10,000 years, 4 millimeters will disappear. About 4 millimeters is just the chemical weathering for climate. Weathering on this. Then we have some inland ices, and then we have some blasting for everything and so on. But just raining on this one, it will turn down about 4 millimeters. How can we know that? Well, you know, for about 30,000 years ago, the inland ice disappeared, it melted from this area, and then the surfaces of all these rocks we have here was flattened. It was smooth and flattened because of the inland ice, which you will hear later on today. In the bottom of that, it looked like a sandy paper, you know, and it was polishing the rocks, so it was smooth and no minerals tops coming up. And then we know that certain minerals, if we go here, those minerals who crystallize at first are also those minerals who will dissolve more easily on the rock's crust, because they are stable at 1200 degrees. And now we have only 0 degrees up here. So they are unstable when they come up to the surface. That's why they are more unstable than quartz down here. So what we have done, we have looked for about 3,000 outcrops, and we have measured the tops, the height of the quartz crystals, and the deep of the feldspar or the micas in this granite, because micas biotite here, and they are more easily weathered. So 3,000 outcrops for, we have put it out a square of 1 square meter, and we have measured a lot of minerals in this square meter, and we have figured out that approximately 4 millimeters during the last 10,000 years have disappeared from the softer minerals in here. So it's just a way to see what will happen to this when it's raining. So about 4 millimeters. This one. It's better to have this one. I have some that one. We have weathering. And the weathering creates these sedimentary rocks. You know, there will be some slates, some sandstones, some limestones, and so. And if you have magmatic rocks, we have also metamorphic rock. And metamorphic rock, it means that those primary rocks who have been pressed together or heated up, and pressure and heat belongs to each other. If I create some heat, there will also be some. If I create some pressure, there will also be a higher temperature in this area. So temperature and pressure is increasing, and then we have a metamorphic rock. So that a granite so if I pressure very hard on a granite, it will be the higher temperature will make this granite to be soft, plastic, more or less, plastic. And when I pressure this one, I pressure it very hard. The minerals, especially the black minerals and the white minerals and the red minerals, they will arrange in lines like this. In this one, you can't see it down there, but you can go up here. This is a gneiss. We call it a gneiss, rock like this. And there we have some splitting up of the minerals. Here is random mineral orientation, but this is not random. It's a very, very, very special orientation of different type of minerals. And that's where we can see that this is a metamorphic rock. But if the metamorphic rock also is weathering, it can rain on this gneiss and it can rain on the granite, but it can also rain on sedimentary rocks. So everything is going away. We have primary the magmatic rocks, because that is the first we have magmatic rocks. When the earth was cooling down, they were building some hard rocks at the top, and there was magmatic rocks. This one was weathering, so that we started to create sedimentary rocks. But it was also pushed together and creating some metamorphic rock. And this is going around in a big circle. Reusing is a very common word in geology. Nothing disappears, and nothing new is created. I almost said, but I said it. But you know, when we had our line, the rope, we started here 4.6 billion years ago. That's the time when we got everything here. Everything which is, you know, we are not collecting anything from there's no spaceships coming in with new material every night, I think, at least. There are some meteorites. Most of the space material, the space dust, everything coming into the Earth is burning up in the atmosphere. Only very, very, very little is coming down to the Earth. So what we got for 4,600 million years ago is what we have today. And what we will have in another 4,600 million years. So there's nothing new, no new material at all coming into here. So this granite or this mineral, they have been here and they have been another thing before. Perhaps they have been, this granite once was back in the 4 billion years ago. It was a magmatic. It was a granite. Then it started to be a metamorphic rock. So it turned in 2 billion years. It turned into a gneiss, and then it weathered. And this granite was a gneiss, and it turned into be a sedimentary rocks, like a sandstone, like this. And this sandstone was a sedimentary rock, probably for about 1,200 million years ago. But pressed together in a rock formation and turned into a metamorphic rock, which is called quartzite. we can say that it turned into a gneiss again. And then this gneiss melted up in another rock formation and turned into this granite we have here. So this can be the third generation of a granite. One of the youngest granites in Sweden is 800 million years old. This is the youngest one in Sweden, 800 million years ago. It was created. But so everything is going in a circle. It's very nice. And also this, if you can see here some tracks in here. There's some worms have been living here. There's fossils. They call it Scoletus worms. And we will see them on Öland, because this one I have picked up from Öland. You are not allowed to bring anything from Öland, but as a geologist I have a permission everywhere I go to put some stones in my pocket, especially diamonds. I once was in a gold mine in Canada on an excursion, and we had to promise not to take anything out of this mine. So they were looking us through when we came up from the mine, and no one has picked something. But when we came up, they said, okay, you will have this one. So I got one and put it in my bag. So I have one piece of gold back home, but it is not so many kilograms. It was very, very little. But as we were very, very friendly to them and not picking stones, they gave us stones when we came up. So Scoletus worms in this one. It's very interesting. Okay, we have magmatic, metamorphic, and sedimentary rocks, and they go create this circle of the rock forming circle. We call it. And so only 3 rocks you need to know. Magmatic, metamorphic, and sedimentary rocks. But then you can see that there's thousands of names of different types in every of these 3 species, but never mind. And we start with magmatic rocks. I think we can have that before a break. Oh, it's so nice to have this picture. This is a diagram which I love. No one can love this one. If we have more than 66% of silica in a rock, a magmatic rock, then we have what we call an acid rock. And the names of the main acid rock is granite. If this granite is blown up, if the magma is blown up in a volcano, so there is no time for the minerals to crystallize. You know, if we have this magma coming up, and there is suddenly the temperature will fall from about 800 degrees to 0 degrees when it comes out on Iceland, there will be a very, 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 very fast cooling of this material, and then we will have this one's material. This is a porphyry. Porphyry is an ashes which have been blown up, and we have small minerals which can be seen. In a porphyry is volcanic acid ash with small feldspar and quartz crystals. We can see them inside here. That is a volcanic ash, volcanic acid ash. We have a lot of those volcanoes around the world, and they are explosive. They are very dangerous for us people as they blow up a lot of ashes, and the ashes fall down, and you can suddenly there's 1 meter of glue in the ash, and this is not so good to be there at that time. That's why they are evacuating people living very close to these volcanoes. And then we can ask, why are people living very close to volcanoes? Because mostly of the soils created by the volcanic ash is very good for growing plants in. So it's very, very easy for people, when it's not a volcanic activity, to stay there. It's easy to feed them. They be wealthy, and areas are very good to stay in. That's why we are staying there. Porphyry, granite, and if it comes into veins, you know, sometimes the magma is coming up. When it's coming up through a solid rock, it cannot penetrate the rock itself. But in the rock, there are always small splittings. We call them cracks or fissures and faults and so on. There comes the volcano splitting up, and then we have something which we call pegmatites for granite. For this, so this is the main, and we have porphyrite, rhyolite. Yes, it's not so common, and pegmatite. If we have this intermediate silica content, 66 to 52%, we have what we call a diorite. When you are going down to Esbø laboratory, down in the tunnel, you will see that there will be a diorite down there. It's more dark than an ordinary granite, but it is not completely black. So it is in between the black one and the red one or white one, and then we have the diorite. This is intermediate, we call it. So Esbø diorite, you will see it when you go out there next week. Sunday. Sunday is the first day out there, huh? Mm-hmm. Yes. Then we have some veins for this porphyrite, and the porphyry, the ashes coming out is what we call andesite, and it's the most common volcanic ashes in the world. Is this andesite. 45 to 52% by silica. We have the basic, mafic. This is the black one. Then, if the lava is coming out like this one, we call it a basalt. And if it is like the granite, it is cooling down. Here, this is a gabbro. This is a granite. This is a diorite. Simply. Geology is very simple science, I think. So, and if it comes into a vein, a diabas, in Sweden, when they are selling, do you know what this is? The black, if you polish them, there's very nice stones, and a lot of graveyards have these black stones when you write your name and so on. And in Sweden they call it a black granite. But it's not a granite. It's a basic mafic one. And have you been drinking a wine from South Africa, which is called black granite? No. Try to find it. It's a very good one, because it's grown on basaltic soil that we call a black granite. So every geologist knows about this. We are drinking just black granite, this wine. It's a red wine, rather dark, but well, if you don't like it, I don't mind it. I have I have no economic interest in this, if you are drinking or not. If there's less than 45%, we have an extremely, this is when we have a crystallization just up here, olivine, and you see, dunite is a monomineralic rock only consisting of olivine. And if this rock is going out for a metamorphic process, it will turn into this powder. So this talc is ultramafic rocks in the beginning of its life, and then it has been pressed together in a metamorphic process, and now it has turned up to be this children's dust. Yes, you can have it. No, you see it, it feels so good for your hands. Ultra basic. So what we have is we have this acidic, intermediate, and basic. And we have granite, diorite, and gabbro. That is what I want you to know about this one. So that we have these three stages of deep magmatic rocks. Now we will have a short break. I think we have to open the windows so that you're not going to sleep. It's better for me if I'm standing up, you know.
Stretching your hands, yes.
Oh, yes, and open the windows. Yes, you can go outside also if you want.
5 minutes, okay?
Yeah.
At 3 we will talk about.
For the water.
Yeah,
Chemical dissolution.
dissolution. Then do you know do you know approximate amount of water that is 10,000 years old is?
Yes,
It's a little bit tons
you
of
know,
water.
in Sweden we have about 1,000 millimeters a year.
1,000 millimeters a year.
Yeah, yes.
And times 1,000 years.
Yes, and 10,000 years. So you can, it's a lot of zeros, yeah.
All right.
So it's a lot of water coming.
Yes, it is, but because it was hard to grasp it that 10,000 years of water
Yes.
is 4 millimeters erosion. That is,
Yeah.
it was hard to think how much water it is going to be.
Oh yeah, it's not much. It's very, very, it's only like this one, 4 millimeters.
But the amount of water that it requires.
Oh yes, it's you know, it's about 1,000 millimeters every year in one spot, yes, and 10,000 years. So it's a lot of liters.
Yeah, it's a lot of liters.
Yes.
It is from Estonia or from
Nej, från Öland.
In Estonia they have very rich
Ja, oljeskiffrarna där. Ja.
burning this, but they are
Yeah.
really like stones also.
Ja, ja.
Okay, shall we get them back? And
Ja, ska vi se hur lång tid har jag? Jag har en timme till. När kommer Jeffrey? Han kommer...
Precis. Nej, han kommer 16.30.
Ja.
Det är mycket tid på sig.
you are 2 timmar.
2 timmar.
2
Ja,
timmar. Så vi har en break
ja vi 3:15 eller något sånt
kvart
där.
över 3. Ja. Okej. Come on guys. Och då har de kaffe där också.
Där nere för oss. Ja, vad bra.
Okej,
Yep.
come in. Guys,
Hey. Okay. We continue with to see where this magmatic rock is created. This is one piece of it can be created in another way also with these rift zones. But you know what this was called? It was called subduction zone, because it's not so very good written. But this is the rock from the oceanic bottom coming down under the land rocks. Yes, where we are living, and here we have some heat depending on friction. When the rock is sliding on each other, there will be a very high temperature melting up the old rocks, melting up the rocks from the bottom, the ocean bottom, that is the basalt, and from this area here, which can be sedimentary rocks, metamorphic rock, or a granite rock. So everything is mixed here. And depending on if there are a lot of material from the oceanic bottom, which is the basalt, this will create a new rock type called gabbro. It's this one here. If we mix it together with material from the crust and from the ocean bottom, we will create this diorite, because then we will have some intermediate rock types. And we are here in this position. And then if we are just melting up the old crust material, then we will have a new granite. And if this granite or gabbro or diorite will crystallize in the fracture zones coming up to the surface, not reaching the surface, in the fracture zones, then we will have this type of, it is the same, gabbro and diabase has the same chemical composition, but they appear in different stages in the crust. And they disappear in zones where you can find some black lines in the rocks. It's, but this is more like a big area. With this is gabbro, and then would be diabase. And if it comes to the surface and runs over the edges of the volcanoes, then we will have a basalt. It's the same, basalt, diabase, and gabbro. It's the same chemical composition, but it appears in different places on the Earth's surface. So it's very simple. And diorite, the same here, and it will call it porphyrite, if it is stuck in these veins like here, and then if it's coming up like volcanic ashes, it will call it andesite. If we go down to, if we go to, this is the typical situation in the South America. This is the bottom of the Stilla havet, South Pacific. South Pacific is going into beneath the coast of South America. And there we have this big mountain range which is called Andes. And there we have some big volcanoes. And we also have outside this Chile coast and every coast, like in this way, a lot of earthquakes. This is why, because the South Pacific bottom is going down underneath the South American plate, and then we have these volcanoes with andesite, and we have inside here, which we cannot see yet, but in 1 million years ahead, we will see this line. And then after another million billion years, we will see these diorites coming up here. And then if it's a granite, it will stay here. And it's like I have got a map which is not so good to look at. It's very, very old, and it's it has been out in the forest, a lot of different excursions, and it has been raining, and that's why it's. And I have another map on the backside here, which we'll see later on. This is a map of Sweden, like this, and we are here in Oskarshamn, like right here, and this is the Öland Island. Sorry. This is the Öland Island where we are going. So we'll pass this strait of Kalmar here, and we go up north like this, and we go back, and we are staying here. And the red here, this is the granite. The yellowish here is the porphyry. And the brownish here is the gneiss, this one. So it's crystalline rocks. All these types are crystalline rocks, but it's different types of metamorphic, volcanic, and magmatic rocks. And if we go out to Öland, you will see that there's sedimentary rocks out there. Sedimentary rocks, so we'll see that. But we have a lot of crystalline rocks in the whole of this. We call it the Baltic Shield, and it contains granites and gneisses everywhere. And this purple area here is diabas. We have it also somewhere, but I will come back to this one. It was moving. You know, everything is moving. Africa is moving, and Europe is moving, and my map is moving. So we call it plate tectonic. Oh, this is a lovely picture, but I have told you about it here. It is the same picture as I have here. So I will not show you this one, but I have it with me if I will lose my concepts, so I can go back to this one. This is as another triangular. I've written down some quartz. We have this plagioclase that is sodium and calcium feldspar. We have it here, and we have alkali feldspar here, potassium feldspar. And then we have olivine, pyroxene, just to see how these minerals connect different type of rocks. Then we have, if we have quartz like this, the quartz and feldspar, and then we call this one for granite. If it's so much quartz, like this down here, and so much feldspars like here, then all this area, so you can see that the granite area, granite can be very different in its composition. Now I only have feldspars in quartz and plagioclase like this then. So I have not put it in some biotites, some different other minerals, but just to see it. And then this is the acidic rocks. And then we go down here, there are intermediate rocks. So we have here, diorite. And then if we go down and find this olivine and pyroxene, we have the gabbro, these mafic rocks. So everything is very close together into each other. And this is the ultra basic rocks we have down here. So gabbro is a very, you see, it can be any composition, almost. It can be very high concentration of olivine. It can be almost no concentration of olivine. And pyroxene can be very high. and so on. And this is a very, very broad broad composition in different types of minerals we call gabbro. And the gabbro could also be a basalt. I could always have written basalt, and then I have to write down here porphyry, and then I have to see andesite there. So you can use this together with this block figures, block names, to see that this is. And if we have this diabase, we have porphyrite, and we have pegmatite instead of these names. So you can use it like this. This is very, very straight lines. I'm proud of this picture. Okay, I will show you some pictures of these granites. I've been holding this in my hand for a very, very long time. This is granite, and you see it can be reddish, it can be almost brownish, and it can be gray, and it can be the color of granite can be very different depending on if there are much feldspar, a lot of quartz, a lot of biotite, and so on. So EFC in this magma, there can be a lot of different concentrations of magma minerals. Can do like this, perhaps everybody can see this. You see, reddish is granite in this one, and if we have this is about from down here up to the north of Sweden. It's about 2,500 kilometers. I think, yes. So it's a very long country, but so the composition in this we call granite is not the same in this place and this place and this place and this place and that. So that it's very different. So that you must know that it's very it's not so easy to say it's a granite and I know exactly what it is. I don't know. I have to go there, and at least some people are sending me stones in some envelopes and they come to me, please tell me what is this, and I say it. Oh, where have you found it? No, I will not tell you. They think there's some gold in it, and always some yellow minerals and crystals in this one, and they say, oh, what is this? And I ask, where have you found it? They will not tell me, because they think that I will go there and pick up all the gold crystals. But then it's mostly granite, and this brownish is gneiss, and so it's crystal, and it's a very complex situation. So if they have decided to create deep deposition, deep deposit here in Oskarshamn, there have been a diorite or granite where you can find it. Up here in Forsmark, which is out here, you can see that there is a gneiss area where they have found a good place for the final solution in Sweden. We don't know if it's the final solution yet, but they are doing some investigations about it there. It's very interesting also if you are looking when you are out driving in your home countries and you are driving on these roads which are covered by asphalt area, you can see that this asphalt is of different color. Perhaps you have not thought about it, but as a geologist, I know that if I go down here, I know that this is a grayish asphalt. If I go here, it's a reddish asphalt. If I go here, it's a white, almost white asphalt. If I go up here, it's a purple asphalt, like this, because they are using the local material for mixing the asphalt. In the asphalt, it's about more than 85% stone, because it's the stone which is strong. The asphalt is just to make it smooth to drive on. So they are taking out. So that is very interesting. You can do some mapping of your own countries just driving along on the roads with the asphalt. It's interesting. Perhaps you don't find it interesting, but I do it. Oh. So this is Sweden. I heard yesterday we had a snowstorm up in the north. It's nice. They are trying to, I'm going up here in a couple of weeks. I will be up here in a place, there's a copper mine up there which have been closed down for a while, but we are going to look at it again. It is called Stekenjokk, and I recognized, and I phoned them in the town of Vilhelmina, and they say, oh, no, it's not more than 4 meters of snow. 4 meters of snow now. So they are trying to open the road, but it is not so easy with 4 meters of snow. You know, you cannot put it away. You have to dig it and take it away to some other place. But I say, you must open it because I'm coming. They say that we don't mind about you. Okay, we got it. This is the granite areas. And this is the pegmatite, and this is the vein of granite, and this is the porphyry. This porphyry here is a young one. This one is from Pinatubo in Philippines, and it's very nice. Porphyry, because a porphyry should be small crystals in a very tight surroundings. So this is the top stone of Pinatubo. I don't know exactly when it was when it has erupted, but a couple of years ago.
1991.
1991, yeah.
I suppose.
Yep. So this is not so old. 1991. You can send it around because it's a nice porphyry. And if we go down to the Gabbro area, this contains a lot of iron, alumina, silicate. But the iron is oxidizing. So this is iron hydroxide. When it comes up to the surface and the rain is coming, we will have some iron oxidized, iron hydroxide, so being like on your cars. It's the same process, so that the rocks are weathering like your cars and bikes and everything like that. I don't think I have this one. Yes, sir, here. This is the Gabbro, which is coming down. And then we have diabase. It's the same. It will be some iron hydroxide on the surface. It's like this. And this diabase is very, very famous. Have you heard about rock wool? No, you haven't been building houses yet. If you are insulating your house, you can have some glass fibers, but you can also have some rock fibers. That is called mineral wool. And mineral wool is diabase. So you excavate diabase, crush it into very small pieces, and you melt it, and then you blow some air into it, like if you go to your holiday with your sugar, you can make some sugar wool. You know what that is?
Oh, yes.
Yeah, sugar wool. But we take this one, blow some air through diabase melt. We will create some diabase wool. This is the rock wool. So, and we are using this for insulating our walls against the cool and the heat. And it's safe because it will not burn that easy. We have to go up for 1200 degrees before it's melting down. So that's why, that's a big industry in Sweden to make this rock wool out of diabase. Basalt is the same. This is the volcanoes material coming out on the surface like this. You can use basalt also for creating this rock wool. Of course, it's the same material and the other way. In Sweden we have a television program which is describing different disasters which will happen to the humanity when we are going to be out of this earth, and we will die, everybody, and then there are all these bad happenings, as we said about when the dinosaurs died. This has happened several times before, that many of the living organisms have been died because of these disasters. And one of these big disasters was at the trap system up in the north of Siberia. It was huge amount of diabase, not diabase, basalt, pouring out on the surface. They call it a trap because they came in different in different positions around the world. It's about 200 million years ago, and then we had a very big disaster. At the same time, we have some small disaster for 200 million years ago down in south of Sweden. It is the same diabases. We don't see the basalt, but we've seen the diabase, because when the basalt is coming up to the surface, it has to penetrate some fissures before, and we only see the fissures here in Sweden. But this is the same age as in the at that time. This was so much of carbon dioxide out in the space, so the temperature rise, and every organism was dying for 200 years ago about. Then we started to some organisms always survive. So far, we have had this. This is not completely dead, but we have a lot of this. So this is very interesting to see. We can see them here because we have a lot of volcanic activity down in south of Sweden. We also had a lot of earthquakes, creating a lot of you don't know. I will take that later on. I'm sorry. I have to make some definitions about different types of fault zones before. So forget about it, we take it later on. Basalt, and then we have sedimentary rocks, like this mudstone, we have claystone, we have slates, we have black shales, we have limestones, we have sandstones, and so on. A lot of stones, bedrock on Earth consist of sedimentary rocks, more than the granitic one, the crystalline rocks. In Sweden we are concentrating on crystalline rock because we almost don't have any sedimentary rocks. It's just on Öland and another island out in the Baltic Sea. So we have three processes. Weathering, And that can be mechanical weathering or chemical weathering. Mechanical weathering is, at least in our areas, is inland ice. It's a big one. It will take about 50 meters during one inland ice to take away everything. So it will be very interesting to see what will happen next time when all the cities is crushed down into small pieces, and you will have Stockholm down in north of Poland. And it's like a moraine down there, so it's not so good for you. So weathering, chemical or mechanical weathering, is very different. Even if you think about, you see root systems for trees, they go down into fissure zones, and the roots are growing, splitting up the rocks. There we call them mechanical weathering. And then the mechanical weathering is opening up the rocks for chemical weathering, so that the rainfall can go down into fissures and cracks, and dissolution will start. And then with the weathering is making small pieces of the rock. And these small pieces of the rock is transported into streams, like Yellow River, Amazonas, Mississippi, Missouri, you name it, Emån in Sweden. It's not a big stream, but you will pass it when on Saturday when you go down to Öland. You will pass one of the biggest streams in Sweden, the rivers. You will be surprised. It's not more than half a meter deep, but there's some fishes there. Salmons is a good fishing place. The salmons is coming up from the Baltic Sea, going upstreams to create new salmons. Up there. They call it, they play. I don't know what we call it. We also go to special places and to make new babies. The salmons do. Okay, that doesn't matter. Transportation in these streams, and we go down to the sea and to the lakes and so on, and there we have some sedimentation. The sand, the clay, you know, the big stones, they will stop very close to the beach. If you go to the beach, you can see there are some stones, we have some sand, sandy beach and so on, there are some stones and so on. That is exactly here. And then if you go a bit outside here, there will be some sand. If you go out here, we will have some clay. So here's stones, sand and clay. So the deeper the water, the more clay there will be. So here we will have some slate, here we will be some sandstone, and here we will have some conglomerates in this area. So there will be a separation of the material. And then we have some limestone. Well, limestone is a chemical dissolution of this air and water combination of carbon dioxide, carbon dioxide in the air and calcium in the water, H2O. So there will be a what do we call it? Utfällning, precipitation of carbon dioxide, calcium carbonate in the water, together with shells from animals living in the sea, from these bones and so on, from fishes and so on. That is limestone, and we were going to see that on Öland. So it can be what we call it recrystallization, or it can be a cementation together, to put it together, because it's sand. It's just sand, and you have a pressure on the sand, and if you unload it, it will still be a sand. unless you don't have any small particle in between the sandy grains. There can be some clay, there can be some calcium carbonate inside, and that is what we call cementing. The sandstone will stay as a stone. The sand will be a stone. But it can also be so high pressure that the sand, the grains will melt just in between when they are pressing for another grain. There can be a small melting process, and this melted go out in the space between the grains to get it together. That is what we call recrystallization. And this is a conglomerate. You see, this is a beach which have been a stone. You see there's some stone, sand. The fraction of sand is 0.2 millimeters up to 2 millimeters. That is sand, nothing else. If you have 2 millimeters up to 20 millimeters, there's some stones. At 20 millimeters up to 200 millimeters, there is some, that is stone. The other is gravel. 2 millimeters up to 20 millimeters, that is gravel. And 20 millimeters up to 200 millimeters, that is stones. And over 200 millimeters, that we call it the block. Big blocks, boulders. Okay, so we have sand and we have stones in this sandstone. And I have a very nice piece of sand conglomerate here. So I will send it around because it's very nice. You can see it's very fine-grained material, and there are some very nice round balls of stone particles inside here. You can let it go around. You can see it's very nice to have a conglomerate. Sandstone, it consists of sand, 0.2 to 2 millimeters of grains pushed together. And in this sand, when you are going out swimming somewhere and close to the coast, when you go out for the deep water, you see that on the bottom you see some small skithögar. There is some worms, sandy worms, sitting in the sands, and they have pushed up some small hills. This is not more than like this. If you can look at the bottom and see that this one, and under these you can see that there is some small worms in the bottom of the sand. These worms were living for 550 million years ago on Öland. But you can still see them. They haven't developed so much, but they are still, you can find them if you just dig there. That's why the birds are going on beaches taking up these worms. The sandstone is very good for the evolution. Sandstone, and then we have sedimentary rocks like slates. That is a slate is like this. It contains of clay, and clay is another part of this micas. So micas is a crystallized clay. So if I pressure this one slate hard enough, it will turn into a mica schist. And sometimes this contains a lot of organic material, like the one you were smelling. And it also contains some animals. Yeah, this is a trilobite. Trilobite in this slate here. You are not allowed to take it with you because it's very nice. I can send it down so you can see that you have a nice small fossil. We will see a lot of fossils on Öland. They're very, very common out there. Perhaps not this one, but we will see it in this limestone. There we will have, this is also a fossil in this limestone. This is an octopus living here for 490 million years old, is it? It's not living, it's not alive. But it lived in this sea, and it died in this sea, and it sank to bottom in this sea, and then there was some lime calcium carbonate cover it, and now we can see it if you go out there. You can see how it worked. It's very nice. We see a lot of them on Öland. They are very, very special for this one. So limestone, it's only in sedimentary rocks you can see fossils. Because if an animal fell down in a magmatic world, it will be nothing left of it. It will burn up. It will be burned down to nothing. But if it fall down here in this sea to the bottom, we can cover it by sand, we can cover it by lime, we can cover it by clay and so on. Metamorphic rock. Oh. That is pressure and temperature is the two main words we must know. If we rise the pressure, the temperature also will rise. So if we press it together, and then if we press a continent together, the material have to do something inside this. So if I have one continent here, or I have one continent here, and we meet these continents, in between these continents there will be something like this happening. And this is what I have been trying to draw here. This is the pressure creating high temperature, and this is what will happen. This is a mountain range, just like this. All mountain range that's in the world is created by this way. Pressures from the sides pushing them up and pushing them down. So if we have very high mountain, we also have a very deep root system down at the bottom of these mountain ranges. We have in Europe now, we have one mountain range going on, just started in the south of Europe. The Alps, down south in north of Italy, in north of Slovenia and so on. There we have these Alps, and that depends on the moving of Africa up to the north, faster than we are disappearing from Africa. So they are 1 centimeters a year, they are coming closer, and they are smashing this together. This process started for 65 million years ago, approximately. So it is very new. It's only 6.5 centimeters on the line. So it's just started, so it will go on. And also we have in Himalaya, this is the same. India is penetrating Himalaya by 11 centimeters every year, if you go a statistic. 11 centimeters. That's why it's so heavy smash down in Nepal for this moment. It's very, very, and they have 8 or 9 on a scale which is called this Richter scale, yes. And it goes from 0 up to 12. If it goes up to 12, there's nothing left. You know, everything is smashed into gravel because it's so very strong. And in Himalaya it was 9, when it was 8 and 9, these two, and it's extremely very powerful appearance of this what do you call it? Earthquakes. And this is the result of these earthquakes. And this is what is happening here. And if in the middle here, in the middle of the mountain range, the pressure is very high and the temperature will rise, so that the rocks in here will be plastic. There will be no fractures, there will be no earthquakes, there will be nothing like that, but it is just smoothly bending like this, folding and bending, because it's soft. If we go out in the outside of the crust, the rock is very hardly pressed, but the temperature is not so high so that the rock is going to be plastic. And then if it's still crystalline rocks and we have this, and the pressure is building up this pressure, and suddenly something happens, then we will have these extremely high earthquakes. So earthquakes, it's happening here, and we have some cracks here, and here we have some folding, softly folding, because it's like when you were young, you were buying some clay to build some animals, to build something. But when you bought it and it was cold, you could not bend it, because then it was falling off. But if you held it in your hand, so you heat it up into 37 degrees, you could bend it like everything. It is what's happening here. It's more than 37 degrees, but it's a lot of, this is processes which is quite normal. So, we have this subduction, we have granite, sorry, we have granite, granite turns into a gneiss. A gabbro, this basic rock type, it will turn into amphibolite. Because when this metamorphic process appears, there is also deliberate some water phase, and this water will go into pyroxenes, and it will react with the minerals in there and creating amphibole. Amphibole was almost the same as pyroxene, but it has an hydroxide ion in it. So that diabase also go to amphibolite. We don't know exactly. Sandstones will go into something like quartzite. It will be almost pure quartz, because the finer sand grain you find, the more quartz is there, because it is resistant into chemical dissolution. Every other minerals in the sandstone will dissolve, but the grains of quartz is still there. So then if you smash it together, it will be a quartzite. Limestone will turn into marble, nothing crazy. And this slate is turning into a mica schist, gneiss, and migmatite. Yes, I will show you some pictures. It's too much Swedish in this one. Let me just tell you, this is the pressure and this is the temperature. And if we raise the temperature, we also have this. This is the. I've seen that the pressure here is 30 kilometers down in the crust, This is 20 kilometers down in the crust. This is 10 kilometers down. So if we go here, we can follow different metamorphic phases depending on temperature and pressure. So if we have high temperature and high pressure, we turn into something which we call anastasis. And this is resolution of the rock. It will turn into a new magma. This is a new magma we have here. And then if we go back, so this is just how to create a sandstone of sand. Here we are trying to make it more like clay is turning into schist, into micas. Here we have amphibolites. That means that pyroxenes turns into amphibole because of water content. So this is just for geologists, so that you don't have to recognize this one. But it's just to see the connection between pressure and temperature. And we go like this. And there we are going to dissolve a new magma. Okay. Mica schist. Mica schist. This is if you have some claystone, this clay will turn into micas, and then we will have this mica schist. I saw that it was not a good picture, but I have a mica schist. It is. If we have this slate and we press it, then it will turn into, you see that this is very dull at the surface. It's not so bright. And this is very bright because it's a micas. So this is the schist, but it's instead of clay, we have some micas here. Mica schist. Yes. Okay, you can come and look at it. And then we turn into a gneiss. That is what we have seen. It's a structure in the granite. In other ways, almost the same content. And this gneiss can be of different types. Sometimes you can see this one. This is it's very interesting because this is what we call it porphyry blast. It has been built. Here you can see that the lines are going around. So this is created because of the metamorphic conditions. So this is feldspars. Feldspars is growing inside the rock, pushing the micas away. So we can see that this is the has been born inside these inside the gneiss.
Maybe on this, what is called masochist, we can make a break.
Oh yes,
15 minutes, and then you will have the nice blocks they are saying.
Oh yeah, I see that they can.
Waiting downstairs.
They are almost dead.
It will be a good portion after that we can go to sleep.
Okay, that's good.
15 minutes. Go down for coffee, please. For cooking.
Okay, we'll start again with this metamorphic rock, which is called amphibolite. And this is if we are pressing together, heating up a diabase, a gabbro, or a basalt, they will all three of them turn into amphibolite. And we cannot really see, if we just have an amphibolite, what type of rock it was before. We know that it was a mafic one, basic one, but if it appears like veins, we can say that, okay, this is a diabase. But if it has been a basalt or a gabbro, can be very hard to see in its appearance. But in the amphibolite, you can see there is some lineation in this area, and so that is one good reason to see that it has been it is an amphibolite. But you can also see there is some red dots here, and that is a special mineral which is called garnet. And it appears very often in amphibolites. So we can see that it is a typical metamorphic mineral. So we can have this, there are 8 different types of garnets, but we can have this as a temperature gradient to see how high temperature this rock was when it was turning into metamorphic stage. So we have different types of garnets, so we can have them as a temperature indicator for the process. So that is very interesting. Garnet, if they are very nice, they can be reddish, deep reddish, and they are almost like a gemstone. You know, you can have some earrings, and you can have rings and fingers and so on, a necklace. They are very, very nice garnets, and especially from Burmish garnet is very, it's reddish and very, very nice to buy. Not nice to buy, not nice to have. And this is marble. In Sweden we don't have so much marble. We have very small amounts of areas where we can find this marble. We have up here in the middle part of just in the same altitude as Stockholm. We have some small area of marble, but it is not of a very good quality. This one is white and fine, but normally it's a greenish mixed with different minerals and so on. We have used it in mortel. You know, when you are crushing some herbs in a stone pot, yes, then we are using these marble pots, yes, to mix it together, and so that's we have used in Sweden a lot of these marble areas. It is not like this marble you have in Italy. It's bright white and very nice, but I think it's Carrera. It's called Carrera marble. It's very, very nice marble. But in Sweden we have this reddish one and a grayish, greenish thing. But still they are marble. And marble is a limestone which have been pressed and temperaturized and come into it. But the same mineralization, the mineral is calcium carbonate. Quartzite is if you are having a sandstone, pressing it together, it will be turn into a quartzite. You will have the opportunity to see one quartzite from the bus on Saturday. We are not going to stop there because it's it's one of the pillars for the bridge over to Öland is standing on this quartzite in the middle of this strait between Öland and Kalmar. It's one nice place, but if you had got north, we have something here up in Västervik, which is about 40 kilometers 60 kilometers north of Oskarshamn. We have some quartzite, and it's bright white stone, very hard, useful for putting into asphalt because it's so white, and because when it's dark and you have to turn on your lights on your car, sometimes asphalt can be very, very black. But if you have white stones in it, it will be bright, and it's very good for this asphalt. So there is one asphalt quartzite quarry up in here in Västervik, two of them, of course. And otherwise, we have also quartzite up here. As I told you, I can see on the asphalt on the streets, we can see what kind of typical rocks we have there. So this is up here. The quartzite is also we use quartzite when we are melting iron oxide. You know this Bessemer method? No. When we are trying to make iron out of mineral magnetite, we have to melt it down, and to lower the melting point, we put in some quartzite in this melting to react with the crystalline rock where the magnetite has as a host rock. Then we are using quartzite to mix with this melting to get out a better quality of this iron. So quartzite is a very good industrial mineral. We use it very often, and also we use it in what do you call it? Fiber optic. Fiber optics. When you are putting some lights into this, this fiber is of quartz. So we can use this in many different industrial situations. Wow! If you know this picture, you know everything about petrology, which is where this is, of course, totally in Sweden. I will explain it very briefly. I'm sorry about it, but this one here is a rift zone. It's in the let us say it's the Atlantic Ocean. In the middle of the Atlantic Ocean, there is a big mountain range. So if the Atlantic Ocean is about 6,000 meters deep, during the mountain range, it's only 3,000 meters. So that the mountains down at the bottom of the Atlantic is about 3,000 meters. And they are all volcanoes. And there is coming up basalt, because it's coming up. And it's a curious thing. We can see when the magma is coming up like this, there will be they will go like a plow. You know what that is? It will go up in the middle and split the ocean bottom. Next time, the next magma comes in the middle and push it away on its side. That's why I've been driving. This is the same magma, and this is the same magma, and this is the same magma, and this is the same magma. So we can see and we can calculate how long time we can also see what, you know, this is the basalt, and in the basalt we have magnetite. So when this comes up to the surface, the magnetite will stay in the direction of the magnetic field on the Earth at that place. But then we know that the North Pole has been changing so that the North Pole and the South Pole has been converted several times. And we don't know when it will happen or when, but we know that if you are looking at this one, we can see that this is the normal North Pole up in the North Pole. Here we have the North Pole at the South Pole, and there we have the North Pole at the North Pole. I think it's about 1 million years it will fluctuate. It's very strange, but it's a very special way. But we don't know what will happen here on the surface when we close down the magnetic field. Then we have no protection from the radiation from the sun. It can be very, very interesting to see what will happen next time.
How exactly did you determine that I mean, did they determine that the poles had been switched, like by looking at the rock?
Yeah, this is called paleomagnetism. So it was the American Navy who recognized this, and it was top secret from the United States because they found it during the end of the Second World War, and they thought that this system with the North and South Pole in different directions was a navigation system for the German submarines. So this was top secret information. So not until 1950, 1955, the scientists, geological scientists, got the information from the US Navy about this, and then we decided to investigate this very closely, and we found it. It was very, very interesting information to know about this, but it was top secret in the beginning. Oh.
What is the name of the method exactly?
Paleomagnetism. Paleo means old, old magnetism.
Okay.
So we can measure this because if we go down and take out the stone, and we have the direction and altitude, we can, and we cannot bring it like this. We have to know exactly the position and the how it got stuck there. Then we can say this is paleomagnetism. So then we can say, and we, first of all, we thought that we saw that there were different directions of north and south and so on. We thought that, oh, the poles have been circulating around the world, but it was not so. The poles have been at the same spots. They have converted to be plus or minus, but all the continents have been circulating around the world. Strange. Good. And this is the subduction zone. This is the deep wells, djupgravar, vad heter det? Deep trenches, deep trenches in the world. You know, outside Japan we have big trenches. Outside Indonesia we have big trenches, and so on. That's here. And here we are creating magmatic granites or diorite or gabbro, and we also have this one, and volcanoes. We have weathering. We have sedimentary rocks, and everything. Everything is in this one. This picture is. So please learn this one by heart in Swedish. No problem. No, sorry. Just to watch it. I think this is a masterpiece of drawing.